It could be worse. You could have I could have adopted you when you were little, and then you would have had me. You would have had me with all that sarcasm. Never know. All right. Well, we got a few people missing today. Looks like a couple of rows missing today.
All the soccer people.
Soccer people, but I got a row missing there.
I think Marley moved back there. And I don't
way back there. All right. Okay. Well, have your exams here. In general, I think the exams turned out really well. So, but I do want you to remember that chapter 1 and 2 just kind of keep recurring. So, Jason, are you open to meeting with students and going over their exam with them?
I can. When would it work for you guys?
No, just individually even. If they were to contact you and say, hey, absolutely, right?
Yeah.
And I would be too. So if you want to go over and figure some things out, I mean, I know you can get the answer, off because I posted the answer key, but more than that, you kind of need to know maybe why. Yeah. But if you miss 3 points, don't come see me. You're fine. If you miss 1 point, don't come see me. You're fine. If you miss 50 points, oh wait, you may not be here today. Gee. Okay. Continue to do the homework. Did I open up chapter 3? Nope. Darn. I'll open it up ASAP. Okay. So we've got some rings. Throw that thing away. Okay, so we got C5H12. C5H12. Let's do all the isomers for C5H12. One, two, three, four, five. You got that one. You got that one. Oh no, sorry, 10. That one. There's a whole bunch of those. That one. Oh. Doop, doop, doop. Doop. Got that one. Yes. That one.
Have rings right at the top? Or is that something separate?
We're getting there.
Okay, sorry. I was just wondering. My bad.
We're getting there.
Okay.
All right, so there's a whole bunch of those. But, and I made the mistake right off the bat here and put a 12. But C5H10 meaning that there's 1 degree of unsaturation. Right? So those have all 1 degree of unsaturation. So if there are more, probably some more. Anyways, if we look at the ring ones, they also have 1 degree of unsaturation. Okay, so they're C5, that's C5H10 if you were to draw out all the hydrogens on there, right? 2 on each one. And then if we want to do them all, we can drop and do a 4-membered ring. Okay, and that one, if I put the methyl group on a different spot, it's the same, right? Then we can do a triangle, but I have to have 2 methyl groups, so I can do that triangle, and I can do that triangle, and then if I do any other triangle, they're the same, okay? What's that? Oh, then I can get an ethyl. The ethyl triangle, okay. So the way this works is, let's think about triangle ane here, okay? Cyclopropane. Yeah. Triangle ane, I just think is,
I like that.
but I do get that So if we look at this, what is the bond angle there? What is the bond angle there? In a triangle, it's 60, right? Well, it's a triangle. So it is 60 degrees. And what is it? What's the hybridization of this carbon? sp3. And what bond angle does an sp3 want? 109.5. Okay? So there's a big difference, actually, between 60 degrees and 109.5. So a cyclopropane is not a very stable group, okay? If I went in the lab, into the stock room, and I found a bottle of cyclopropane from 1950, it probably wouldn't be cyclopropane, okay? It would have done something else. If I order one in straight from Aldrich and get it here, it's probably good for a little while. But if we were to run a lab even next year, probably I'd have to order new stuff in. It's just not super stable. And the reason is because those bond angles aren't real good. So if I were to look at this a little closer, is this a good pen? If I were to look at this a little closer, I've got my carbon and its hydrogens. No, that's not a better pen. And I've got my carbon and my hydrogens. And I got my carbon and my hydrogens. And I got to get my other two bonds going, okay, to each carbon. If I put the bonds directly, they're 60. But if this is the shape of an sp2. If I put them out like this, my great little drawing here, okay, and then I look at my overlap between the orbitals. My overlap is not great. Maybe, some in there, some in there, some in there. The overlap between those orbitals is not optimal. Okay? But now you can see that my bond angle between, not necessarily if I draw a straight line, but now my bond angle gets closer to be 109. Okay? Maybe it's 105 or something. But what the molecule will do, what the bonding will do, is it'll sacrifice some orbital overlap, okay, some sharing of electrons in order to form that bond, okay, if you force it into it. So we call this is an example of bent bonds. Okay, so those are bent bonds. We go to the next one. Did all the moon cake get circulated? Has everyone had a bite? Yeah?
Did anyone not get any?
What do we think? Eggs maybe in there.
Occasionally it has like egg yolk in it. Oftentimes it's made out of whatever they like. A lot of desserts are made out of red bean, but this isn't red. But it kind of still tastes like it.
Like a beans? I think this is does this taste like beans? You get them beans.
A little. It tastes a little bit like red bean, but it's also not red bean. I'm not sure if they. Did you make it?
So I've been to China quite a few times. I'd like to lead another student trip to China. Take organic chemistry and go to China.
Okay.
That'd be fun.
Go study.
Look for the trip. Okay, so if I expand this out one more, what's my bond angle here? 90 degrees, right? And it still wants to be 109. But it's a little bit better. But here again, that bond angle is probably going to be more like 100. or somewhere in between 90 and 110. Okay, so cyclopropane, cyclobutane is not that great either, but it's better, a little bit better, a little more stable than cyclopropane. So if we move to the next one here, okay, turns out if you draw that flat, what are the bond angles? Gosh, now I got to do math. What's the bond angles there? Figure that out. It's what is that? All right, figure it out. Google has the answer. No, it's going to be like all right, someone will figure that out. But if you look at it, sideways, if I were to flip it over and kind of look at it sideways, what happens is it kind of flips up this part of the ring here. So it kind of takes this and it flips this part of the ring up or back. That's kind of this part here, okay? And when it does that, it kind of gives a little twist to it. And then all the bond angles come out to be about 110. They actually turn out to be pretty good. Okay? All right, what's my answer?
108-ish.
108-ish? Okay. So these are 108-ish. All right? So pretty close to 109. But you get that little flip and you can get a 109. So cyclopentane is actually a very stable structure. You'll see it in lots and lots and lots of places. Like, the sugar of DNA is a pentose. Okay? So, all right, so let's move on down. Okay, do your magic again. What's my bond angle? 120? Okay. So my bond angle here is 120. Oop, not Celsius, just degrees. And so now we're getting a little bit past. We're getting on the opposite side of where we were with cyclopropane and cyclobutane. We're getting to where those bonds are kind of folding into each other. So in order to get that bond angle back down to 109, it adopts a different conformation. It adopts a conformation. See how cyclopropane kind of had one lip go up? This one has a lip go up and the other lip go down. Okay? And we call this a chair. Actually, they're both chair, but we call this a chair conformation. Like what I'm going to do when I get home. I'm going to get in the chair and I'm going to lay my feet down there and kind of have a recliner type position. Okay? All right, have I lost you yet? Completely? Okay, not completely, we're okay. All right, so getting some groups again, and put six carbons in a chain together. Let's see if there's 6 carbons in there. Going to be a group here. You guys going to be a group? Maybe you can share back there. We'll see if there's enough. Einstein, did you see what Einstein was carrying around? He was carrying around all the carbons in the whole department. See if you can get 6. The blue ones work the same. So the blue ones will work the same.
Six carbon?
Yes. Okay, I have my 6 carbon here. Six carbon. This right here. Build this and build that. How many do we have? Can you guys get another one going maybe, or is there enough carbons? You can use blue. Blue will work the same.
See if we can do this. There we go.
I don't know if silver will work.
Silver? Do they just need 4?
Silver works, yeah.
Oh, it does?
They're
Okay.
good.
Some of them.
That turns out to be a tetrahedron. So you got a 6? You guys got a 6? Do you guys have a 6 back there? Or you just kind of like try to share? Need another one? Get one more going for those guys. Not right now.
I just like the dog.
Okay, so here we go. It should look like this. Now make it flat. Make it as flat as you possibly can make it. Make it as flat as you can possibly make it. So of those that are making it flat, what happens when you're making it flat? What can you feel? What can you feel happening? You hit some tension. In chemistry, we call that torsion. But yeah, it kind of wants to fly apart a little bit. Okay? It's actually hard to get that completely flat. Now, the other thing is, look here. When mine's flat, okay? So if you look at this carefully and you look down one of the bonds when it's flat, look down one of the carbon-carbon bonds, what do you see? What do we see? They're all eclipsed. All the hydrogens are eclipsed. Okay? All the hydrogens, for you playing soccer, all the hydrogens are eclipsed. All right? I tell them that I won't count them absent if they win, but if they lose, it's an absence. So, did they lose?
We lost yesterday.
Might as well not have gone. I don't know. Sarcasm. Sarcasm. Don't tell your coach. So if I take this and I push one of them up and one of them down, okay, kind of do that with yours there. And if you want to throw a few hydrogens on there, go for it. But if you do that, you push one of them up and one of them down, now what happens to my hydrogens right there? They are what? Staggered. They become staggered. So it does two things. One is it relieves some bond strain, okay? And it frees up it gets these hydrogens a little farther away from each other. Okay? So it's much lower in energy to have this in this chair conformation. What we're going to call it chair conformation. Okay? So there's lots of chair cyclohexane type rings in biology, and most of the time they draw them flat. Okay? But every so often, like if you look at the structure of, if you look at they have to be completely saturated, so they have to be all sp2. So if you look at some structures that are not, sp3. If they're not sp3, then they become flat for other reasons. But if you start looking at some three-dimensional structures of those biological molecules, you'll see that it's like in the crystal structure, it'll be in a chair conformation. Okay? All right, everybody see that? Okay. Do you think you can draw a chair? Think you can draw this chair? So draw that chair, a nice big chair, right in your notes or on a piece of paper. Pretty close, not bad. Okay, draw that big chair. And then we're gonna do some. You got a chair? You got a big chair drawn? Okay. Oh, you got a chair. You're gonna use that one? Okay.
How big is this chair?
Pretty big.
Like full piece of paper big?
If you want. But we're gonna add stuff to it. So you gotta be able to see it. Okay. So I'm going to add what I'm going to call all the axial positions. I'm going to say hydrogens. So, but it's all the axial positions. Axial typically means, in an axis, right? So all the up and down ones. This is where you're going to just get a lot of points or lose a lot of points. So if you just kind of learn this and do it just like this, you'll you'll not lose points where you shouldn't lose points, and you'll get, like for students, points equal money. So like if I were to pay you, we should do it that way, You get no scholarship. You get 0 scholarship when you come to college, and then depending on how your first exams go, you get some money back.
I think just on top scholarship.
Well, how would I make a salary? I mean, you don't care. You don't care. All right. Okay, so let's do all the. Are we ready? This is an axial hydrogen. Okay. This is an axial hydrogen. This is an axial hydrogen. This is an axial hydrogen. Okay? Now, there are 2 more that you're not going to, if you were to look at your model, they're there just like that, but you're going to not want to do this. This one is up. This one is down. Okay? It's just the problem that happens when you have a 2-dimensional drawing. So if I take my big cyclo here and I'm going to put it into that up and that down. Okay? So here it's back behind the board, basically. This hydrogen is back kind of in the other room, but it's going down. And this one is coming up. So if you want to get your models and kind of confirm that to yourself, this is how you're going to get a lot of points. Okay? Now I'm going to put all the equatorial hydrogens. Equatorial. Oh gosh, how do you spell equatorial? It is an I. Okay, there we go. I'll delete that off the video later. Okay, so every carbon has 2. Every one of these carbons is going to have 2 hydrogens, right? So the equatorial ones are like this. Okay, these are the easy ones here. It's okay. Now, okay, so everybody sees those? That makes a lot of sense. The next 2 are not going to make much sense. Okay, the next 2 you're going to go, I don't get it. But they run like this. Does that make sense? Okay, good. Good. So, meaning, if I put this like that, see how this is a blue one up here. See how that blue one's kind of going kind of that way? And then this one is coming kind of down this way. Doesn't it look like a chair? Lazy boy chair?
I'm not a scientist.
What would you name it? Let's rename it. What would you name it?
More like a lightning bolt, to be honest.
No, you can't be a boat because something else is a boat. A bug? A bug conformation. Is that more descriptive? Yes. We're getting there.
Oh, okay. That's where the chair thing I got.
No, that's the part that's going to blow you away.
That's great.
Okay? Everybody good with this? This is how you're going to get a lot of points. Just know this, okay? Like your middle name. Be able to just do all those, okay? Now, molecules are all in motion. Molecules are always in motion. So this molecule is in, and it's in equilibrium, okay? I haven't done this for a whole year, so I'm going to give it my best shot. Oh, not bad. Got it pretty good. I'm going to go a little higher here, maybe. There we go, that's better. Okay? It's kind of a skinny chair. But it's not the same.
Did it actually get smaller?
I did not spin it.
Did it get smaller on purpose?
No. No, I could not make it smaller on purpose, but it did not spin it, okay? I didn't just take this and spin it. In fact, I did it to where now all of my axial hydrogens are the blue ones. I'm going to draw that one a little bit long because I had a skinny ring. It's okay. You'll be okay with it. If you get a skinny ring, I'll let you do that. Okay? And all my equatorial ones are now red. So all of the equatorial hydrogens become axial, and all of the axial hydrogens become equatorial when it does what we're going to call a ring flip. So this is a ring. We're going to do a ring. We didn't rotate it. We flipped it. We did this flip. Okay? So if you have it like that, well, I actually had it like that. So I had that up, this down. So what happened is I did not rotate it. That's what I did not do. What I did was I put this side down and this side up. And then you kind of let it kind of work its way in there. Everybody do that? Do that with your model. Do a ring flip. Do a ring flip and notice that all the axial and all the equatorial hydrogens switch.
Can you flip that one again?
Try it with that one. You're gonna borrow that one. If you need to switch, put it like a, push that end down and the other end up. There, you did it. You did a ring flip. Everybody should try that. If not here, somewhere. One side went down, this side went down. So this carbon, maybe if I did it this way. If I said, if I were to say that, if I numbered these carbons, let's say that's 1, 2, 3, 4, 5, 6. Now my numbers are, this one is 1, 2, 3, 4, 5, 6. Okay, so this carbon actually becomes this one. Well, you could have started anywhere. I just started number 1 there. You could have started anywhere, but I'm just saying that this carbon, if I tag that carbon, now it's that one. Okay? All right? Oh, we are recording. All right? We good with that? Everybody try it? Okay. Now is where we're going to get a little bit more complex. So we're all there, right? We're all there, right? Okay. So, if I have, that's not that great. If you won't make fun of mine, I won't make fun of yours on the exam, because I. So if I were to have this as, if I have this group axial, that becomes equatorial here. So just a group, this one is axial, this one is equatorial. Okay? And I give that an energy diagram, and I measure it. I can measure it. This is the axial, and this is the equatorial. So there's some energy difference between axial and equatorial. Okay? There's an energy difference between them. And we chart this out. If x equals, okay, x is hydrogen. Well, I'll do it this way. And then this is going to be energy in kcals. Okay, or it doesn't matter, whatever the energy is. I think it's kcals, I'm not sure. So this is the energy difference, okay? It's going to be lower for equatorial always, except for hydrogen. Hydrogen's the same, there's no energy difference, okay? If I put a fluorine on there, the energy difference is 0.2. If I put a bromine on there, it's 0.5. If I put a methyl on there, it's 1.7. If I put an isopropyl on there, it's 2.1. If I put I'm running out of room, but that's okay. Phenyl, it's 2.9. And if I put a tert-butyl, okay, a tert-butyl, it's 5.4. So let's put this in perspective. I think these are kcals. If you look in the book, it's either kcals or kilojoules, okay? We'll say they're kilojoules. I don't know, doesn't matter. Is it kcals? Dang it. How many kcals are in a carbon-carbon bond? Form a bond, how many kcals do you get? How many do you think? Give me a guess. Jason, what is it? You're going to grad school. You got to know these things. I think it's somebody Google it. It's in the hundreds. Okay. So I think it's like 260, something like that. So we're talking hundreds. So we're way far away from that. We're only at 5.4 kcals. Okay? But there's this little thing that says 1 kcal, I guess I did have kcal here, is worth 85% difference. 2 kcals is 97% difference, and 3 kcals is 99.4%, which means that if I have 3 kcals here, or 2 kcals, so right in here, those are in excess of 90% always in the equatorial position. So 90-some% of the time. It's never going to be 0. It's never going to be 100 and 0, because there's always some motion. But 99.4% of the time, it's going to exist in this equatorial form versus the axial form.
A carbon-carbon bond is 80 kilocalories. No. 80 kilocalories.
Oh, okay.
And 900 kilocalories. Not 900, 290.
90?
90, and that same one.
All right, we're still a lot more. All right. That's what Google's good for. Okay, so you see that there's got to be some reason, right? Anybody see a pattern? Anybody see a pattern over here that would give us some reason? I mean, that's really what is going to be useful. Any pattern there? Yeah. Oh, okay. So here I have a difference in energy between two states, right? If that energy difference is 0, then this, if that energy there is 0, then really this equatorial is up there, right? So if this is 0, I'm 50-50. Because it doesn't matter. It could be axial, equatorial, it's the same energy, right? But if it starts switching a little bit, if this is 0.2, then it's not 50-50. If it's 0.5, it's a little bit less than that. And then you get up to 1.7. So now we're up to the place where we're 80 to 90%. So if you have a methyl group on there, you're up at 80 or 90% that it's going to be equatorial over axial.
Because that's how big of a difference it is.
I'm getting there.
It's going to be equatorial over axial.
Equatorial is going to be more stable. I'm going to tell you why in just a second. But do you see a pattern here? Which is bigger, hydrogen or fluorine? Actually about the same size. Trick question. What about a bromine? Bigger, okay? Chlorine's a little bit bigger, a little bit bigger. A methyl group's actually pretty large, if you think about it. A carbon, and then it's got these 3 hydrogens really pushing out there. So its space is pretty large. Isopropyl, bigger. Phenyl, a little larger. And then this tert-butyl, if you were to make a tert-butyl out of those, you could find all these hydrogens and everything. It makes a pretty big group. Okay? So, you guys are wanting to know why, right? All right, so let's pick one. Well, it'd be way easier if I did it here. Let me do it here. Let's take this hydrogen here and let's make it, let's take this hydrogen, which one do I want to do? Do I want axial on this side? I want axial on this side. And I'm going to make this really big group. So that's a tert-butyl. I'm going to make it that tert-butyl, really big group. Okay? And then if I flip it, which one is it? If I flip that one and this one. Carbon 1, and it's red, so it's this one, right? Now, doesn't maybe look quite like this in that drawing, but let's pretend this is a tert-butyl here, and you could put a tert-butyl on yours. Let's pretend that's a tert-butyl. So this is going to be this one right here, okay? And I got this up here. This tert-butyl comes in very close proximity with these two hydrogens. Okay? You guys see that? Back in the back there? This comes in pretty close proximity to these two hydrogens. Okay? This is my tert-butyl group. Got that over here? So these are, you know, up here, the tert-butyl group here, it's pretty close. If I do the ring flip, just did a nice ring flip there, that tert-butyl group kind of just hangs out into space. See that? He just goes out into space. So he gets away from those hydrogens. And so it has less steric strain, less interaction with those other hydrogens. Okay? So it's at lower energy. Not a lot lower, but enough to where it's going to exist over 99% of the time in this locked conformation with this tert-butyl equatorial. Okay? If it's a fluorine, you know, it's going to be like 55% or so. Okay? Just a little bit more. But if it's tert-butyl, it's going to be a lot more. Okay? Questions on that? Good question. That's a very good question. Just don't let me brush over that this is... We got that now? Kind of get that? Okay. All right, so I'm going to show you one thing here, and here again we're going to go just a little bit deeper. Okay, go a little bit deeper here. You ready? Let me redraw this guy here. And I'm going to draw that hydrogen, and I'm going to draw that hydrogen. I'm going to say that that hydrogen and that hydrogen are trans from each other. Okay? Those are going to be trans from each other. And this is going to really, you're not going to believe me, but so this is axial, this is equatorial, this is axial. I'm sorry, this one's axial, and this one's equatorial. Now you're not going to believe me, but unless you look at the drawings, look at the models, but these are cis from each other, meaning they're actually on the same side of the ring. Okay? So if I have you might need the models on this. I'll flip it over. There we go. That's better. So if I look at this hydrogen here and this hydrogen here, they're obviously on the opposite side of the ring. Here's the plane of the ring, like this. This one and this one are going to be on the opposite side of the ring. So we're going to call that trans. Okay? This one and this one are actually, they're not they don't look as opposite, but these are actually on the same side of the ring. So this axial one and this equatorial one is on the same side of the ring. This one's pointing down. So that's definitely on the opposite side, right? But axial to equatorial, they're on the same side of the ring. Or to draw a plane of symmetry between here, this gets put in the same, this equatorial hydrogen gets put in the same plane as this axial hydrogen, and so they're on the same side. So we're going to call that cis. Yeah.
So then two equatorial hydrogens would be trans as well.
Right. So here's an equatorial one, and here's an equatorial one. And see how the plane cuts those in half, and this one's in the bottom and this one's in the top? So they would be trans as well.
So the ones that are on opposite sides of each other are trans, and the ones on the same plane are cis.
Okay, however you want to work it out in your head. Because that is true, but that may not be the way it all works out in your head every time. And we're gonna but hold that. Yes.
So then if you look at the 3D model versus the 2D model on the board, the equatorial are all 3D.
That's how I do it. So if I draw it flat, I could say, oh, this one's coming forward. Let's say it's a methyl group. And I'm going to put this one over here. That's going back. Okay? That one's coming forward. That one's going back. Obviously, that's trans, right? You know, obviously, this is trans, right? And if I did the opposite of that, and I put them on the same side like this, you're going to say that's cis for sure, right? You're not going to, no one's going to dispute that. But when we try to put it into a three-dimensional structure, that's going to become a little more so I have two methyl groups here, okay? It doesn't matter where you start. I'm going to number this one 1, 2. You could number it the other way if you wanted to, okay? Just doing this, and I'm going to number this one 1, 2. And it does not matter how you start this, okay? And it does not matter if you put the methyl group axial or equatorial to begin with. Okay? Does not matter, because it can do a ring flip. This is how I do it. This is when I was deep down in the basement working through sapling problems in 1984.
There wasn't sapling.
There were computers in 1984, but I did not have one. Okay, they would fill up this room. There was no sapling. I was just working these homework problems out of the back of the book, and because there was no sapling, there was no Chegg, so you couldn't buy the answers off the internet either. Actually had to work them out, figure it out. And they had a thing called an answer key that you could work the problems and then drive to University of California, San Diego, and their library had the answer key, we found out. Okay? Just to check to make sure you had this right. So, however you're going to do this in your head, this is how I figured it out. I take the first one and I just say, it's equatorial. I just go, oh, it's equatorial. And if I go, this is just how I do it, okay? If I'm walking around a ring, I go from axial to equatorial, or I go from equatorial to axial, it's cis. Okay? So I'm going from I'm going from equatorial. So if it's cis, this would be, if it's cis, it would be axial, but it's trans, so it's equatorial. I'm going to tell you why I did it that way in just a second. So here, if I do the same thing, this one gets opposite, okay? Because it is trans, so it has to be equatorial axial. Okay? So, the reason why I do it that way, and just figure out a way that works for you, okay? But your way of doing it has to be foolproof. It can't like work half the time. Right? Because you're guessing then, right? So it's got to work every time. But I do it this way because a lot of questions on Sapling or from Dr. Nogales or from other places will say, give the most stable conformation of this cyclohexane. Okay? Well, I know if I start off with it being axial, I have a great chance of it being wrong. So I'd just make it equatorial from the beginning and then do the rest. Okay? I also start off with the largest group. So if this had been, let's say if this had been a tert butyl up here, or a phenyl, I would have put that first at the equatorial position, because I know the biggest group is going to like weigh in on this more than the smaller groups. Okay? All right. Class is over in 2 minutes, minute and a half. Yes?
So then you could draw the axial and equatorial things with the triangles and the lines.
With the what?
I don't know what they're really called. You just draw triangles and lines on the left.
Oh, wedges and dashes?
Yeah.
But that would not be in their three-dimensional. This puts them in their three-dimensional structure. Yes, you can. And if you look up sugars, for example, you'll see them this way and you'll see them this way.
Yeah, but I'm saying if you had it in a chair,
Can I go back?
can you draw off of the chair the dashes and
No. Do not. Do not. Great, great. Oh, yes. Thank you. Thank you so much. That will get you no credit. 0 credit. -10. Do not put wedges and dashes on a chair.
Okay.
Do not do that. That is not how we're representing this. Do not put wedges and dashes on Newman projections. That's not what we're doing. You only do wedges and dashes when you're drawing the molecule flat on the board or on your paper. What's that? Instant fail.
You get an F on your
This tells me you don't know what you're doing. Right? I mean, so do not do that. Okay.